And I'm almost done with this web page. We have discussed in the last lecture, we have discussed this El Niño phenomenon that is quite interesting because it's important. It influences many parts of the world. We will now discuss which part of the world are influenced by this phenomenon a little bit. And it's also interesting because it's one of the few phenomenon really on long time scale variability that are quite well understood. Quite well understood in some sense. We understand the mechanism. Still, prediction of this phenomenon is very difficult for like more than maybe 6 months or 1 year ahead. If we are close to it, then we have quite a good idea. So for a 3 month prediction of the ENSO phenomenon, it's possible. Also because it's relative persistent, depending on the season a little bit, but in general it's relatively persistent. So once it's there, it's unlikely that within 3 months the ENSO has vanished. So it's quite a slow phenomenon. So once we are close to it, already persistence of this phenomenon gives us some predictability for some other climate events. But the real prediction of like 1 year ahead is still very difficult and is still under research right now. Okay. So why is this important? This is a map that you can find in many places on the web. If you do a Google search on El Niño influences or El Niño teleconnections, you will find kind of these kind of maps. So this is a map that in some ways shows us what is happening all over the globe during an El Niño event. So these dashed lines here means that there are increased rainfall. So in the central Pacific, you get increased rainfall, which is due to the increase of sea surface temperatures, essentially in the whole central Eastern Pacific. So why do you think the rainfall is not so much increased in the Eastern Pacific, where actually most of the sea surface temperature perturbation during an El Niño event occurs? Do you have an idea? Sorry?
Is it because of the temperature?
Yes, it's because of the temperature. It's because of cold water. So rainfall, kind of, we have a guess of that. Rainfall essentially depends on how much energy there is at the surface for then convection and rainfall activity to occur. So the Eastern Pacific is so cold that essentially there's not enough energy available there for convective events and for rainfall to occur, even if we have a positive sea surface temperature anomaly. Maybe you can have El Niño events where the sea surface temperatures are so much increased in the Eastern Pacific that even there we can have rainfall events. But typically it's shifted with respect to the sea surface temperature anomalies. The rainfall perturbation is shifted to the west because of the warmer sea surface temperatures we have there on average. You will have to wait until Adrian's lecture on how convective rainfall is actually created for the full explanation of why this is happening. So ask Adrian. Remember to ask Adrian Tompkins in his lecture on atmospheric introduction to the atmospheric part, why during El Niño events there's more rainfall in the central Pacific than in the Eastern Pacific. Then this is almost trivial because this is really where the perturbation of sea surface temperature is. So it's almost a trivial response. And also, we're in the middle of the ocean, essentially, and there are a few islands maybe, but essentially, humans are very little affected by this anomaly, on average. So we're in the middle of the Pacific Ocean, and very few people are living there. These other anomalies that are kind of on the side of this, so to the east and to the west, we find negative rainfall anomalies. So this is, again, rainfall anomalies. So we find a drying in the Amazon region and a drying here, including the islands here, Indonesia, Australia, and some other places. So we get a drying typically in these regions there. This is very important. And this is why the first time the El Niño phenomenon has been discovered, because it has caused this drying in South America, Central America, in these regions. And people were concerned about this, of course, why the rainfall is reduced, and people depend on rainfall, of course. We all need water to drink, so rainfall is an important resource for us. So we rely on this, and this is a very important reduction phenomenon. There are other places, North America, we find a reduction of rainfall, increase of rainfall in these regions. A very, very well investigated phenomenon is this in some places and in some season. This is in the boreal winter season. We find an increase of rainfall here in the southern Indian region. But in the northern Indian region, we find a decrease of rainfall in their monsoon region. So the people of you who come from the monsoon, the Asian monsoon region, you will know that during El Niño years there is a reduction of rainfall in the South Asian monsoon region, mainly the Indian monsoon region. It depends a little bit really where you are. And there are further connections over Africa. So my personal research is actually partially related to these, to understand, to provide mechanisms to investigate these teleconnections, because they are far from trivial to explain. So this response very close to the sea surface temperature anomaly is straightforward to explain. All the other anomalies are far from very easy to explain. So you have to make a theory why this is. I can try to give an explanation. The responses you find here in North America are probably the most easy ones to explain, because they rely on. So what's happening during an El Niño event is this influences the whole column of the troposphere. So you get the warming extending all over the tropical regions. The whole troposphere, up to 10 kilometers, 15 kilometers, is warmed actually during an El Niño event and cooled during a La Niña event. And this causes perturbation to the wave activity. The solutions of the thermohydrodynamic equations in the atmosphere support many wave solutions. A very famous one, the most famous large-scale wave solution, is called, and if you come to our diploma program, this is for sure something that we will discuss there extensively, is called Rossby wave. A Rossby wave is the most prominent wave that is relevant for the very large-scale circulations in the atmosphere. And this is essentially governed by the Coriolis Force. The Coriolis Force is the most important force for these waves. And these waves travel around the globe, essentially along great circles. So the shortest distance on a sphere is a great circle. I call it. It's not a straight line between here and there, but it's if you draw a point here and want to know the closest distance, then from here to there on a sphere, it's kind of it's not just a straight line. It's called great circles. It's kind of curved. And so these Rossby waves are excited by this perturbation. So the perturbation in sea surface temperatures causes adjustment processes in temperature and also is a source for this wave. So this energy that is released there during this El Nino event is released from this location in the Pacific, in the Central Pacific, is released. It spreads all over the world by wave propagation mechanisms. And the most straightforward one to explain and easiest to understand is this Rossby wave that is excited. This Rossby wave propagates northward over the North American continent, and then propagates backward to the equator. And the position of this Rossby wave causes also temperature and rainfall anomalies all over the globe. And these anomalies that you see here in this positive rainfall anomalies that you see here are related to this Rossby wave that is released by this ENSO phenomenon. And other waves are then responsible for the precipitation responses that you see in other regions. So for example, for the Indian monsoon, El Nino is one of the most important predictor. You call it a predictor. So if you have an El Nino phenomenon or a La Nina phenomenon, there's very high seasonal predictive skill for rainfall for the Indian monsoon. So the Indian monsoon can have a failure or can have a good year according to what is the El Nino condition or La Nina condition in the eastern or central Pacific. It's a very, very powerful tool to make seasonal predictions. So this year there is still La Nina, I think. Not 100% sure actually. So that would mean there should be a good year for rainfall in India. It's not that easy though, because El Nino is not the only phenomenon we have in terms of sea surface temperature perturbations. There are many other that may interfere with each other. So you have to really be very careful to make a seasonal prediction just based on El Nino. But it's probably the most powerful predictor for many events. The tropical storms, we don't go deep into this because I want to touch on another topic in this last lecture. Tropical cyclones are influenced by ENSO also. Obviously, because increase in surface temperature make the energy available for tropical storms also increase the energy available for tropical storms in some regions. In other regions, it's not the sea surface temperature perturbation, but it's again the perturbations that are caused by these waves to the atmospheric state that are relevant for modifying the probability to get a tropical storm, for example, in the Atlantic region. So it's not the temperature perturbation, but maybe other perturbations to the winds and so on that are relevant. So this phenomenon, even though it is the local feedback is local, it's kind of So the most important feedback is a local feedback to create this phenomenon. But this phenomenon influences climate all over the globe because of the wave propagating processes we have. So the energy released is essentially radiated away. This is like if you drop the same as if you drop a stone in a tank of water, and you get wave propagation away from the source of energy, from the primary source of energy. That's what's happening also. That's what's happening on a very large scale, in a much more complicated way during an El Nino event.
So, could you write roughly the structure of this famous Rossby wave?
The structure, the dispersion relationship.
Maybe, okay. This famous Rossby wave.
Mm-hmm.
Yeah, just to have some.
Let me see. The structure, you mean?
Just the wave equation or the wave function.
Okay. I will try, yeah? The dispersion relationship, I can write it down immediately, okay? So the phase velocity is equal to the mean. This is the mean flow in zonal direction. So there's essentially here you take the mean flow really average between the surface and maybe 10 kilometers, which is typically for almost all latitudes that we are looking at, it's a westerly flow. So it's flow that goes from the west to the east. Minus beta over k square. So this is simple. This is just the k square plus L square, actually. So these are the two wave numbers in zonal. These are the two wave numbers in zonal and in meridional direction. So it propagates obviously in meridional and in zonal direction. And beta is an abbreviation of what we call Coriolis Force is typically abbreviated with the Coriolis Parameter, which is F, which is 2 omega. This is the rotation velocity of the Earth times sine of the latitude. So this is the parameter that appears in the Coriolis force that is then multiplied by the velocity. And this beta is the meridional derivative of this f. So then this f parameter is not a constant but depends on latitude. And this parameter here is the crucial part. Otherwise, without this effect, Rossby waves would just propagate with the mean flow. It's a very simple thing. But due to the change of the Coriolis force with latitude, we have this interesting wave phenomenon that propagate in meridional and in zonal direction and are influenced by this, how this parameter is changing in meridional direction. This is the most simplified form that you can derive from a very simple equation. The real Rossby waves, and this gives you a good view already on Rossby waves. You can have a more complicated case where also mean flow in meridional direction has to be taken into account, and they can also propagate vertically, and then you have to insert here also a vertical wave number. So this is the most simplified one, the first order approximation or zero order approximation to a Rossby wave. Okay, this is and it's based essentially on you can derive this most easily from the equations of motion. You derive a vorticity equation, a prognostic equation for the vorticity, and this equation allows you to derive this dispersion relationship, linearizing, and so on. You know all the processes as a first order approximation. Yeah. Yes.
So it means that without the El Nino or the La Nina phenomenon, it becomes difficult to predict the climate in other regions of the world.
This is, I think this statement is true. Yes. Most of the seasonal prediction skill at the moment, this is kind of a statement that I'm giving now here. Maybe some other scientists would say, oh, well, this is not true, but this is my opinion. Most of the seasonal prediction skill at the moment relies on the El Nino phenomenon. And this also explains why in Europe, here in Trieste, there's very, very little seasonal prediction skill. Because unfortunately, I mean, this figure doesn't even contain all of the teleconnections. But even here in Europe, there's nothing. look, in Europe there are many other regions where there's nothing. If you look more carefully, actually, and even I was involved in some research on this, you can find also some teleconnections in Europe, only that they are so weak. You have to use a model to really identify them as statistically significant. So it all in the end depends on, there can be some influence of ENSO on Europe, but there are so many other influences that are important for Europe, that this small influence that you have and that you can prove is there is not sufficient for us to predict the climate for the next month even. So yes, I would say this is true. So our seasonal prediction skill at the moment essentially relies on the predictability of ENSO. Yeah.
I see that almost the dates of the increasing of the rainfall. Is it that the rainfall is translating from one month to another, or
Mm-hmm.
is just appearing from nothing?
It's also a very good question, actually. So, okay. There are some very simple answers to this. ENSO was discovered during DJF, so northern winter. That's the season, autumn and winter, northern for the northern hemisphere. For the southern hemisphere is then spring and summer, obviously. Is the season where the ENSO amplitude peaks. So you get the strongest ENSO amplitude in those seasons. If you draw, however, a diagram where on this axis you put the season, so this is January and so on, then you get June and December in the end. And on this axis you draw the standard deviation of the sea surface temperatures in the Eastern Pacific, which is a measure of the strength of ENSO, if you want. Then you find, yes, it's strongest in this season, and it goes down in summer and becomes larger. So it's like 1 Kelvin here, and then it goes down a little bit, maybe 0.6 or something. But the fact is that ENSO is there, essentially, once it's there throughout the year. So what this tells us that, for example, even though the strongest influence, this will be always there. You see, this here for summer, and essentially I can tell you that this response here you will have throughout the year, maybe slightly shifted in the position. So whenever there's a sea surface temperature anomaly at any season in this region, you will have a perturbation of the rainfall because it's always raining there. The thing in this region is that in DJF it's dry, very dry. So you don't get any, even though there's ENSO in DJF with the strongest amplitude, you won't get any perturbation of rainfall here simply because it's too dry. So the same reason essentially why you don't get any rainfall here. It's simply too dry. Even though if you kind of have some trigger that potentially could cause a perturbation in rainfall, it's not enough actually to trigger rainfall. But in summer, even though the ENSO amplitude is weaker typically in northern summer, JJA for example, June, July, August, then is when the monsoon season is, and we will discuss in a minute the seasonal cycle all over the globe. That's when it's raining in this region, and when it's wet. And then this trigger, this perturbation from ENSO is enough to cause variations of the monsoon rainfall here. And the same is true for all the other, also for this, for all the other areas that you see. So the season when ENSO influences essentially depends on when is the rainy season in that region. Okay, that's the simple answer. That's a very good question. I want to stop here now. I'm sure no one else understood, but even I. Can you just speak a little bit up? Otherwise.
So we see the effects of ENSO. So how do we relate the measurement of the ENSO effects over land and over sea surfaces? For example, over sea, we said we can use the sea surface temperature.
Okay. Yes. So they are also a very good question. So some of these rainfall influences that you see here are caused by sea surface temperature perturbations. Others not. So in some regions, it's actually the sea surface temperature that is relevant, like in this region. In other regions, it's not neither the sea surface temperature nor the land surface temperature that is relevant, but it's the stratification of the atmosphere that is relevant. And again, you probably have to wait to understand this. You probably have to wait, first of all, for Adrian's course, who will explain that the stability of the atmosphere depends on its temperature change with height. That is relevant, and that is influenced by ENSO, for example. But there are other mechanisms that can cause a rainfall perturbation. But it's a little bit complicated to explain. For example, these here are not related to stability, but more likely related to rising or sinking motion that is relevant for these Rossby waves that propagate and cause rising motion and sinking motion. And rising motion typically because of the cooling of the rising air. The water vapor that is contained in it cannot be in a water vapor phase at some point anymore, because that's telling us an equation, the Clausius-Clapeyron equation. And then the water vapor has to condense and causes rainfall. So whenever these Rossby waves gives us a reason to believe, the position of the wave, a reason to believe that there's rising motion on average, then you will get a positive perturbation to the rainfall. And where there's sinking motion, you will get a negative rainfall perturbation. So it's, that's the reason why it's very complicated. In some places, it's simply the sea surface temperature perturbation. But in other cases, it's complicated, much more complicated. You have to analyze.
Okay, here when we see the picture roughly, if there is a rain and then in the nearby there would be there draw something solid line, right?
Yeah.
Yeah, in the nearby.
Yeah, solid line is drought. Yeah.
Yeah, but I think it looks as if those things go together. If there is some rain and then in the nearby there will be some drought. But in the right hand side there is some dispersion. I mean, it's not like as if they're together. And when we see the period, there is some difference in the period. One's up here first and then next it will appear the other one.
Yeah. That's probably again, if you look at this and at this, it's probably again this when is the monsoon season that is relevant to say, okay, there is rainfall, there's a lot of rainfall in that region. It's not the only explanation. As I tell you, there are research papers, many research papers explain these teleconnections. It's sometimes not that straightforward. Here it's very straightforward. Here you can almost immediately give an explanation why there should be a drought here. Simply because of continuity. If the rainfall increases in some place, that means there's actually convergence in this place and also convergence of moisture. Then there will be divergence in some other place. That's pure continuity. So there must be some kind of very local adjustment processes, which we essentially see here. Then the other reason, as you well point out, they have more complicated explanations. So it's not that straightforward. They may appear even in... So it's not that here, this is immediately related to that. They essentially appear together. In these regions here, it's not necessarily the case. They rely on... This, for example, here, is the same what I mentioned to you before that is relevant for this, also appears in the southern hemisphere. You get a Rossby wave. that actually propagates also along a great circle, and at some point influences South American monsoon. It's the same situation. That's all quite interesting. I would actually like to show you a figure of this Rossby wave. Again, so you're asking, and it's something that I like very much. I will see if I have actually one. This is, I can show you this. This is actually a real, taken from real observations or reanalysis, what we discussed already. A composite of what happens during El Niño in DJF. So this is not some sketch. This is what was really observed. And you see this rainfall anomaly in this region and the drying in the surrounding. And here you see nothing over India because it's the dry season, for example. Yeah. But this is immediately happening. You see also this is immediately happening because of this Rossby wave. You see an indication of the Rossby wave here, actually. This circulation here is caused by this Rossby wave propagation. It's there's even a nicer Rossby waves. You see, this is the governing equation. This is the vorticity equation that we linearize. And you see, I wasn't lying. This is the equation. And here is a different field you can look at. This field is actually we call it geopotential height. It's something very similar to the surface pressure. Let's say it's the surface pressure for interpreting it. And here you can actually kind of try to follow this maxima. So the ENSO perturbation, in fact, in this case, it's an idealized ENSO perturbation, just in this box. In a model, we prescribed a sea surface temperature anomaly and let a model calculate the Rossby wave propagation, the stationary. And we see this. We try to identify where the Rossby wave actually moves. And one of my collaborators came out with this. I'm not 100% sure. Actually, I would probably not go like this. But anyway, so this is how the energy is radiated away from this region. You see where we are. This is North America. Here we are in the Central Pacific. And here we have this this is a low pressure caused by this propagation over the Florida region and the Gulf of Mexico, and that's causing the increase of rainfall there during ENSO. And so this is what you can do. I want to, the remaining part, which is not much, I want to give a presentation about the seasonal cycle or the annual cycle. How temperature and other variables change because of the radiative input we get from the sun at a certain location on the Earth, essentially depending mainly on the latitude where we are. Just this, it's a trivial. So this is kind of the trivial seasonal prediction what we discussed again. It will be warmer in summer than in winter, but I like this topic because this is actually the largest climate variation we have on Earth. And this variation that we have in many regions, not in all regions. If you go very close to the tropics, There may be other variations that are perhaps larger, for example, ENSO. But in almost all other regions, the annual cycle or the seasonal cycle is the largest climate variation that you can find. So interannual variations are much smaller than the seasonal variations we have every year in almost the same manner. And climate change predicted variations are much smaller still than the seasonal variations we have every year. So it's kind of perhaps nice to understand how these seasonal variations work. Just look at it at slightly more details. And the presentation I give is on my webpage. So it's ICT users.ictp.et, then tilde Kucharski, then annual cycle again my name, this time with the e.ppt. If you don't find it, you can just drop me an email and I will. I was hoping it's already listed here, but hopefully. Okay. So this is this presentation. Okay, so what's the reason for the annual cycle? Of course you know that. The Earth is rotating around the Sun, right? That's what we by now know. And the Earth is rotating around itself. And the rotation axis of the Earth rotation around itself is tilted with respect to the rotation axis with which it's rotating around the Sun. And that causes that in the December period, if we look into this graph, we get more solar radiation on the southern hemisphere. We know all it depends on the angle with which the radiation hits the surface. What is the energy we can really receive? So it's more energy is received by the southern hemisphere, whereas in June, more energy is received by the northern hemisphere. And so this is the simple explanation why we have the seasonal cycle. But you knew this already. Okay, this is just to show. And so we want to understand this is a very simple explanation, but we want to understand what is happening at the Earth's surface and the climate in general as response to this radiative forcing. And what we first look at here is really the radiative forcing, the solar surface radiation that is here actually measured. Again, it's this reanalysis product that we look here. So it's the best estimate of measurements that we have. Again, taking the last 50 years into account, perhaps. And in all the first diagrams I show you, on the x-axis we have 1 to 12, which means January, February. Here's June, July, August, and so on, December. And it's from the South Pole to the North Pole, 60 North, 60 South, going beyond. And it's a zonal mean. So the first pictures I show you are zonally averaged. So we just want to simplify the picture and say, okay, the forcing, the external forcing is mainly governing, or it's only governing a change in the meridional direction. That's the reason why we look at this. So the energy we get, according to the picture that we have just seen, is depending on where we are in the season here. So in June, we get most of the energy from the sun at the surface at around 30 north. The astronomic formula would give us 23 point something degrees, but this is measured solar radiation. So this is also influenced by the cloud cover and other things. And almost symmetrically here in January or December, we get the strongest radiative influx at the surface at 30 south. So this is what we expect. And there's almost nothing in the winter hemisphere. Really no. So the very strong forcing of our climate system, from nothing to 240 watts per square meter. The units are watts per square meter. So it's really a huge perturbation. Think of it when you don't remember, but we were talking about radiative forcing of climate change, CO2. There we were talking about 2 watts per square meter. That's the climate change forcing we are talking about. Here we are talking about, in the seasonal cycle, of a forcing of 240 watts per square meter. That's huge. So the first thing we can look at, okay, that should somehow influence our physical understanding, clearly tells us if we heat a body dependent on the location, what we expect is a temperature adjustment. Any physicist would immediately like to write down a diffusion equation or something like this. You have a source, and then you can maybe solve the problem by assuming a simple diffusion problem. Of course, on the Earth, it's much more complicated because there are all these waves. It's a fluid, so it's not that easy. But anyway, we have some kind of idea. If we heat a body at a position, that should be the position where we find the highest temperature. If not, something very strange is going on. We are physicists, so we expect something like these things. And if we look at the sea surface temperature, indeed, we find that, of course, in June and July, it's warmer in the northern hemisphere than in the southern hemisphere. So there is this perturbation. But if you compare that to the solar radiation, it's much smoother. So the excursion to the north is much weaker. We find the largest radiative input at 30 north, we have found, but the largest temperature still sticks relatively close to the equator. The same is true for the January, December, February, January season. That's one observation we can do. What do you think? What do you propose as a reason for this? Why is this the case? Why is the highest temperature on average not observed at 30 north? Can you make a guess? This, as physicists, you should be able to make a guess, actually. This is the surface temperature, ocean and land together, actually. But I think your question points into the correct direction. It's the thermal inertia, mainly of the ocean, actually. So it takes so long to warm up, on average. We mix here ocean and land, and what I say is only mainly valid for the ocean, because land we warm up quite quickly You may see this even in summer, of course, in Trieste. The land surface warms up within a few days or something. But an ocean surface has a large thermal inertia because of mixing. You mix a huge body of water, maybe 50 meters, maybe 100 meters, depending on where you are. So it takes a long time. It takes so much time that the short maximum peak in radiation is not enough to warm it up so much that we find the highest temperature. So the highest temperature just goes a little bit south and north of the equator depending on the season, but doesn't manage to get to this region at all because it's not long enough. The mean heating is not long enough to cause this perturbation in temperature there. It's the inertia, the simple inertia of the ocean that is relevant here. People live in extratropical coastal regions will know that in Trieste the effect is there, but it's maybe less. But in people who have been in Britain, in UK, the amplitude of the temperature is very much reduced. Summer and winter, yeah, there are differences. But since you are surrounded by ocean, this amplitude is very much damped. We will come to this picture later. So this is the reason already. So the system is not just reacting simply to the forcing, but of course has its own, in this case, simply inertia. You can explain this by simply inertia. But there are very important deviations from that due to the fact that we have land surface distribution, and that's actually part of the explanation for the monsoons. We will see this later. And so things get even more complicated. So temperature was already a little bit more complicated than just the solar radiation we measure. Another parameter which is very important to understand circulations, rainfall distributions, and so on, we are concerned with is this surface pressure or sea level pressure, we call it here. Sea level pressure and surface pressure is very similar. It's the same over a flat surface, but over mountains we kind of interpolate the value to a imaginative zero level in order to compare values. So it's a little bit of a tricky thing to look at the surface pressure. Just imagine that the Earth is completely flat without mountains. Then surface pressure and sea level pressure are the same, which for most of the Earth is actually true where we have ocean. And the surface pressure actually has low values where we have the warmest temperature. That's the simple explanation for this is that warm air weighs less than cold air, and therefore we expect where we have the warmest air on average, we have the lowest pressure, because the surface pressure is a measure of the integrated mass that we have at that position. That's another equation that we do not write down explicitly here. Then, interestingly, we have this in the southern hemisphere. I'm not even sure if we can trust this because there are so little measurements going into this that I would exclude this from the discussion. So there's very little structure here, and I believe this is due to the fact that the model essentially does what it wants. And anyway, there's the Antarctic continent here, and this interpolation there to the surface of this variable may be questionable. But in the northern hemisphere, it's perhaps more interesting. And anyway, if we focus on these regions, with this high pressure, we see this high pressure region at around 30 north, which is strongest in the winter season, as you can see, and weakens in the summer season. This is already something we cannot easily explain by the energy input. We have to study climate dynamics if you want to understand this. But we have already made a picture of this essentially when explaining the ENSO phenomenon. Because we've discussed, we have to have the lowest pressure at the equator, and then there's higher pressure to the north of it. And these high pressure regions are the subtropical high pressure regions. So they are there. And then to the north of it, we find again lower pressure, which is related to the westerly winds we have on average in the region, for example, where Trieste is, particularly in winter. So in winter, we here already in this latitude, we are on the edge between the high pressure system and the low pressure system. But on average, we are in winter. You know this, and even yesterday, sometimes in summer, we are influenced by these cyclones that are moving in the westerly flow, and that can be described also to a first order by Rossby wave propagation, for example. So the equation that I eliminated. So things are much more complicated already. Things that, however, have to adjust to the surface pressure is the winds. Surface pressure and winds have a very simple relation if we are interested in first order effects. And the reason is an approximation that we make to the momentum equation. So the first order approximation for if we are away like already 5 degrees from the equator to the full momentum equation, which contains many terms, is that the pressure gradient force is in equilibrium with the Coriolis force. So pressure gradient and Coriolis force, they are in an approximate first order equilibrium. And from this equation, then you can immediately derive that the wind has to be parallel to lines of constant pressure. So the mean wind that we have, maybe not so much very close to the surface and not so much at the top of the troposphere, but anywhere in between, the mean wind we observe is in very close approximation parallel to lines of constant pressure. And that's the reason we have these. This is actually only the zonal component, the only component that makes sense in a zonal average. So we have between the high pressure in this region and the low pressure on the equator, we have a negative mean U component at the surface. And that means we get have easterly winds. This is driving our ENSO, kind of the mean state we have in the Pacific, the easterly winds, the wind that blow from east to the west. To the north of the high pressure system, because of this equilibrium, which we call geostrophic equilibrium, the wind direction has to change, so we get westerly winds in our region. The same is true for the southern hemisphere. You see there's this, it's all blue here, essentially between minus 30 and plus 30 degrees. So this is the region where we have the trade winds. Between the subtropical high and the equatorial regions, we get these trade winds that blow and blow and blow and blow. But here is a change of sign. You see, northern summer, there's actually here, this is a positive component. So there is a period, if we come into July, August, where even on the zonal mean, we find a reversal of the trade winds and they become westerly winds. And this is actually an indication of the monsoon circulation. So this we cannot explain easily by the energy input from the sun directly, but we have to take into account land-sea contrast, and we will look at this in some other slides. So this is a very interesting deviation we get due to the land-sea contrasts, actually. This small whites, this could be something related, actually, the same phenomenon in the southern hemisphere, but much weaker, because essentially from a very first order, we have less land surfaces in the southern hemisphere. Therefore, this effect is weaker. But there is some tendency for a weakening of these mean winds. This is the rainfall that is associated with this. And also, as you can see, the rainfall follows this low pressure. That's also a good rule. Rainfall follows the low pressure, essentially. The reason is that if the wind were in perfect in this equilibrium between pressure gradient force and Coriolis force, then you would not expect necessarily the low pressure to be associated with rainfall. But at the surface, we have another force that becomes important, which is friction. So the frictional force in the end causes that if you have a low pressure, that is happening what we expect to happen, that the air is flowing into the low pressure. That's the equilibrium really at the surface. With the component also following the other forces, but still there's a net component flowing into a low pressure, from the high pressure to the low pressure. And that's the reason why where we have the low pressure, we get the largest rainfall amounts. Then we have a decreased of rainfall. So this color here is decreased rainfall in the subtropical high pressure, and again increased rainfall in our westerly zones like Trieste, where we are influenced by these waves that move in the westerly flow. So now I will show different maps to look into a little bit more details about this land-sea contrast, for example, and a little bit more regional detail. So the maps that we will look at for the rest of this presentations are essentially we look at a mean, a DJF, so the maximum perturbation in one direction we can get from the seasonal cycle, and a mean in JJA, and then we look at the difference. So this is the difference between this map and that map. To kind of to amplify the differences due to the seasonal cycle of the energy input from the sun. So the main features we have discussed already before. So it's mainly warm at the equatorial regions, independent of the season, and cooler in the extratropical regions. It's cool here in the Eastern Pacific, and we have discussed this in detail why this is the case. So we don't have to discuss this anymore. Now let's look at the difference, which is the amplitude of the annual cycle, if you want. And what we see is essentially what we have mentioned before. We see a huge amplitude over land because of the inertia of the land surface is much less. So if we calculate the body that is typically affected by the annual cycle over land is a much smaller amount of soil than the ocean surface, which is mixed because of the volume that is mixed. So you see it's a huge difference in the annual cycle between the ocean surfaces and the land surfaces. So the land surfaces gives you some kind of a potential. What is the potential effect we can have from the annual cycle? And you can see in some regions in Asia, we find almost 40 degrees temperature perturbation. Whereas in the same latitude, so we expect the same forcing in principle to act. We find over the sea surfaces some values between 2 and 5 degrees only. So that's the reason I mentioned before in UK, for example, it doesn't make so much difference if you travel there in summer or winter, because if the air is moving from the ocean, you get always very temperate air. So this doesn't make any difference. Whereas if you move to somewhere in Asia, it will make a huge difference when you go there because there's a huge cycle. And you also see this in a slightly less clear way in the southern hemisphere. Whenever you have a land surface, the annual cycle is increased. In the tropics, it's very weak. That's what we also expect, but it's also interesting anyway. And so this different land surface distributions in the hemisphere actually leads to the fact that even the global mean temperature has an annual cycle. So the global mean temperature is warmest in June or July and coldest in January, simply because of the different land-sea distributions between the northern and southern hemisphere. You can work that out, that this should be the case from the picture that we have seen before. So it's quite interesting. Even the global mean has an annual cycle, which you would expect in a more simpler system to be maybe cancelled out, but it isn't because of the different land surface distribution between northern and southern hemisphere. Let's look at the surface pressure. The surface pressure is always a little bit more complicated than temperature, but essentially follows in some ways what we have seen before. So in DJF and in JJA, we find for example, always low pressure, our low pressure systems close to the equator. They move to the north in JJA. But a very huge change, let's concentrate on the changes, we see in Asia. So if we compare here northern winter to northern summer, then we get a huge high pressure. Or if we do the opposite, we get a huge low pressure in this region. And essentially this change is causing us the monsoon, the Asian monsoon. And also this change also influenced the African region and therefore causes the African monsoon in some ways. It's more clear for the Asian region though. So this is the change of the winds that eventually then causes the monsoons. If you look at this picture, for example, on average in summer we have this situation, high pressure at around 30 north and low pressure further to the equator. But in the Asian region and extending into Africa, this is actually reversed. We have the low pressure over the land because the land warms up a lot. The air becomes very light compared to the ocean, to the Indian Ocean in this case, close by, and we get a reversal of our wind direction because of this simple effect. So it's the land surface distribution is a very important impact, has a very important impact on our mean climate, and causes this reversal that the monsoon, the name monsoon actually comes from reversal of winds, essentially. That's the origin of this name. And the reason is that between summer and winter we find a huge thermal difference between the Asian continent, and therefore cause huge pressure differences in that region that turn around the winds if we go from winter to summer, which you can see here. If you look into the northern summer region, we find rainfall in this region. Whereas if you look into the winter season, there's no rainfall in this region. The reason is exactly what I told before. We get this low pressure in that region because of the heating up of the continent, and then the wind flows in, converges, and causes rainfall. And again, the differences between these two again highlight the monsoon regions. So these are the main monsoon region, where you find the largest annual cycle in precipitation. In this case, over Africa, the same is happening. We find There's a huge shift of the rainfall if we go from one season to the other. You see this here, this dipole. We have the main rainy season maybe in JJA, north of the equator. And then if we go to DJF, we find the main rainy season south of the equator here.
Question. Can we go 2 slides back?
One more.
Is there near Eastern Africa and difference? This yellow part, why is it not uniform? Eastern Africa on the lower figure. Yes.
What is here?
Yeah, it's not uniform. Since it is on most of the equator, I expect it to be white everywhere.
Okay. Yeah, this is not the case everywhere, as you can see. In this region, so this means that DJF is warmer. It's a positive. So DJF is warmer than JJA. One should look into why this is. One potential explanation would be the shift of the ITZZ. So maybe if it's raining a lot and there are a lot of clouds in JJR, and these clouds are absent in DJF, then you may expect an increase of surface temperature, because this is surface temperature. This would be my first guess why this is happening. Yeah, there can be in surface temperature, there can be some interesting variations that we can see here. So my guess is that essentially it's during summer, of course, in the Saharan region we find a huge temperature anomaly. But in this Eastern African region, since the ITZZ, the zone where it's raining, is in this position, maybe that decreases the temperature here that much that, yeah, it's even colder than in the dry season, actually. So where are you from? Is it like that? Is what I said true? Yeah, so sometimes the surface temperature is a forcing of rainfall. Sometimes the surface temperature reacts to changes in rainfall and cloud cover. So it's a non-trivial relationship, surface temperature, particularly over land. Over sea surface, over the sea surface can be also complicated, actually. Not always the surface temperature is the driving mechanism, can also be a reacting mechanism. But over land surface, in most cases, the surface temperature, maybe not in most cases, but can be a reaction to what is happening to the rainfall. This is a complicated relationship. Here we zoom in because I personally worked on the Asian monsoon, so I zoomed in here on the Indian monsoon, actually. In this figure, again, we draw here January, February, and so on to December. And we go from southern 20 south to 40 north. So we zoomed in on the monsoon, and we averaged in the zonal direction in the monsoon region. So 70 east to 95 east is the cutting out India, essentially. And you see that in the winter months here, it's dry, obviously. And then as May comes, there's this sudden northward. It goes first gradual, but then there's this there are some regions where it starts further north earlier. So it's a very sudden influx of these monsoon rains. Then it stays and then gradually decays and moves again to the southern hemisphere. So it's just it's heating the land surface, and then suddenly the monsoon sets in. And this is the zoom to the, again, looking at these two seasons, winter and summer for this region. And it's essentially dry here in winter, apart from the southern part, which for some people is important, of course. And then in JJA, we get this influx of the winds. Can you make a guess why there's this maximum rainfall here? So the bluer the color, the more rainfall. Can you make a guess? The wind direction, yes. So these arrows, sorry, I didn't explain that well. These arrows is the wind, the mean wind at this close to the surface. So the wind goes like this. This is the monsoon, southwesterly monsoon winds.
Maybe it's related with that point when the wind is changing.
Yeah, so the wind is already a good answer. And the second is that there's a small mountain here, the Western Ghats. It's a mountain, not very high. So in coarse models, you almost even don't see them, which is a problem because then you don't get this right. But it rains there more because they act as an obstacle to the flow. So what does the flow do? The flow has several possibilities, can try to get around. But one other possibility is that it goes over the mountain. And as it goes over the mountain, the air has to rise. And that, again, gives us reason for condensation of the water vapor because the air cools off. So that's the reason why we see this maximum here.
I think in that region there are lots of chains of mountains, I think.
Yeah.
High, yeah.
In this region, not very high. The Himalaya kind of starts maybe here, and you see at the ground of the Himalayas there's another peak of rainfall. But in this region, the mountains are maybe 500 meters,
500?
not much higher. Yeah, almost like in Trieste, we definitely see this phenomenon because if we have winds, southerly winds, at least not necessarily at the surface, but you can have this even if there's border like northeasterly winds at the surface, but already at some higher level, at a few kilometers, you get southwesterly winds. Then this little mountain chain here definitely causes an increase of rainfall, even for Trieste. This little lifting of 300 meters can be very powerful. And here we see a simple, the same simple mechanism.
I think Everest is somewhere around there, maybe above.
The Everest? Yeah, the Mount Everest, well, the Himalayas, I think we can see here. Is this. The Himalayas we probably see in the temperature. Yeah, so the Himalayas obviously are here, where it's relatively cool, because it's up in the mountains. So the foothills would be where we find this increase of rainfall, but it's to the north. So it's here. This would be the increase of rainfall due to the convergence at the foothill of the Himalaya. But even though the Himalaya is so much higher, since the winds are already quite weak there, the effect of this little mountain that is just in this very strong flow is more relevant, actually. Similar effects you may have in Africa. I'm not so good in the geography, actually, but so what is this? This,
There is a mountain, I think.
this is a mountain.
Topography is not stable. There is a large variation.
Here could be, here.
There is also forest, a lot of forest.
Anyway. So there are, I will not go too deep into this. This is just go through it. Mechanism for the monsoons, essentially. So people think you may have you experience probably in daily life land sea breeze. You know what that is. When it heats up, you're living to a coast, close to a coastal place. During daytime, the land heats more up than the sea. When you get wind from blowing from the sea to the land because of the pressure adjustments, you get a circulation. At night, the opposite is happening. Kind of monsoons are the simplest explanation is them to be a huge continental scale land sea breeze. So in summer, the northern land areas heat up more than the surrounding ocean, depending now exactly where we are looking at. So for South Asia, that means the Asian continent heats more up than the Indian Ocean, for example. And that causes this essentially a continental scale land sea breeze that leads to increased rainfall over the land surfaces. Europe. So I did this figure myself, and I was surprised when I prepared this because I didn't expect that. That actually in Trieste, we are in Trieste. According to this figure, if this data, one has to be a little bit careful with this rainfall data. This is, again, the arrows are the surface near wind, and the colors is rainfall amount in millimeter per day, which is a unit that we typically use. Millimeter, you can really see it, millimeter. So yesterday it probably rained, my guess is more than 20 millimeter in one day. So that's much more than the average we see here. But if you look, for example, to Trieste, which is here, according to this mean map, it seems that it's raining much more in summer than in winter, which is not what would you have guessed that? So maybe one would have to be a little bit more careful. But I think the general tendency is, again, that even the European continent gives some kind of, the heating of the European continent gives some kind of, there's no monsoon, obviously, in Europe. People would, what is that, monsoon? But based on this, one could almost say, oh, there seems to be something like a interesting seesaw if you look in winter and summer and compare that. In winter, the Mediterranean is very wet. In summer, the Mediterranean is very dry. But actually, there's a lot of rainfall over the land surfaces. So it looks some kind of monsoon phenomenon even in Europe. But obviously, don't tell that anybody, even though it's filmed. But it's quite interesting. And if you look at the difference, actually, you see something that looks like, almost like the monsoon. It's definitely forced. These differences are definitely forced by the increase of land temperatures. One thing that we have to take into account here is that here we look at the rainfall amount, average rainfall amount. When it rains in Trieste, for example, in summer, it rains very rarely in summer. Maybe less than once a week or something typically. But when it rains, because the air in a warmer air can contain a lot of water vapor, rain can be very heavy. So within one day you can have 10 times as much maybe as in winter typically. So in winter it can rain all day long, but it's kind of more drizzle, and so the total amount is much less than what you get from a thunderstorm. So that can be part of this kind of strange feature that it seems that Trieste is much wetter in summer than it is in winter, which intuitively, I mean, in summer there's almost the sun always outside, but not always. And so when it rains, it can rain heavily, and that gives us this interesting seesaw. Again, the pressure systems, so part of this can be explained by the movement of the high pressure systems. So in the general structure of the pressure in winter, typical structure is that we get high pressure in the Mediterranean and low pressure in the North Atlantic. And that causes us, because of this equilibrium, the geostrophic equilibrium between pressure gradient force and Coriolis force, southwesterly winds in Europe. Then there can be some breaks into this here in the Mediterranean, and we get some of these waves that are included in this flow move into the Mediterranean actually and cause perturbations. And in summer this is kind of disturbed potentially by the fact that we have the heating over the land surface. Yeah, this is zoom into the Mediterranean when it rains. So the Mediterranean is dry in summer, but to the north it gets monsoon-like, quite wet actually. So this is an average, essentially 10 east to 30 west. So it's really the European region where we find this interesting feature. Oh, there's carbon dioxide. Even that has a seasonal cycle. As you can imagine, plants are growing in the respective spring season, depending northern hemisphere, southern hemisphere. So when they are growing, they are absorbing CO2 and creating oxygen, and that reduces the CO2 concentration in the atmosphere. So when we are talking about this increase of CO2, we are typically, of course, talking about the annual mean. But in the annual cycle, that can vary, of course, because now, in the period now, CO2 is reduced because of the growing of the plants. And in winter, of course, autumn, the opposite happens. So that causes us an annual cycle of the carbon dioxide.
Sir,
Yes?
is that the main reason for seasonal cycle in carbon dioxide?
Yes. That's the main reason. You see this when you look at data, obviously, that there's but the trend that we were discussing so long, human-induced, is of course visible. And is in this case stronger than the seasonal cycle. And this is the end of my lecture, I think. Okay. So at this point, we are done. And Riccardo Farnetti, a real oceanographer, will take over, and since this course is called Ocean, the ocean part, will tell you much more about the ocean than I did. I preferred to concentrate, if anything, about the ocean, on the boundary between atmosphere and ocean, because that's the only thing I know more about. But if we go deeper into the ocean, unfortunately, I know very little, and so Riccardo will tell you in the next 2 lectures all about what you ever want to know about the ocean. Very interesting.